Alright, so let's get started with today's class. So what have we seen so far? We've seen some basics of quantum information. We saw a few quantum algorithms and we tried to develop an understanding of when it is that quantum algorithms are more powerful than classical, right? And the big breakthrough of quantum algorithms so far is, breaking modern day cryptography. So that's sort of the big buzz, and that's what we're going to try and understand next. So in order to do that, as I promised you last time, what we'll now do is we'll kind of switch tracks to cryptography a little bit. We'll try to understand the number theoretic assumptions that underlie cryptography. We'll try to understand how security is argued, and then we'll switch track back to quantum and come back and break it, because unless you know the significance of what you're breaking, I think it's much less fun, right? So let's go like this. So today's class is little bit of a fun class. We'll go over some concepts in cryptography. In the beginning particularly, I wanted to convey to many of you that cryptography is kind of far beyond just encryption, because it always hurts me a little bit when I ask people, what do you know of cryptography, and they say, there's like these two people and there's a channel and there's someone listening to the channel. I mean, this is very primitive. It's like from several decades ago, much before even I was born, let alone you. So let's try to first of all update our understanding of what it is, and then we'll come back. Okay, so yeah, so this I'm sure everybody knows. So it's a mathematical science of controlling access to information. And at a very high level, what you're dealing with in cryptography is methods for protecting privacy, integrity, but still having some functionality out of any system, right? So I always make this remark whenever I talk about cryptography for the first time, which is, it's very easy to be perfectly correct and insecure. This is by not using any cryptography, and it's even easier to be perfectly secure and not correct. This is by just not doing anything. So that is the easiest of all. So obviously the whole deal is about how to get the best of both. So what are the things that we would like to achieve, right? So let me show you some interesting examples of some of the very cool and surprising things that we can do in cryptography today. Yeah, so this is the first most classic example, or well, one of the most classic examples, which is multi-party computation. So what this means is that, let's say that you have elections and you want everybody to vote. You could do various things. I mean, we have voting booths right now and so on. You could imagine casting a vote sitting in your house, or even in a voting booth you could be casting the vote online, and what you would like to do is that everybody should be able to cast their vote, right? And you should of course get correctness, which is that you should get the right output, and you should get security, which is that individual vote privacy should be maintained. Okay, so the second one is protecting your code. This is a really exciting one. So let's say that one of you, let's say, discovers a better algorithm to factor numbers classically, right? And by the way, it's possible. Okay, so we'll talk more about the hardness of factoring, but let's say that you discover this. Now you could be a geek like me and try to write a paper about it, or you could be more enterprising like this student here and decide that you want to sell this code, but you don't want to leak the algorithm. So what might you do? Well, again, cryptography comes to your rescue. So what we can give you is a program that's called an obfuscator. What this program will do is it will take as input some code and output some kind of garbled code. Okay, so we, let's call it obfuscated code, and this code should still produce the correct output, but it should be impossible to reverse engineer. So when you look at the code, even the binary, so even from the binary of the code, there are multiple ways of trying to go back to the original code, but there should be some mathematical guarantee that you cannot learn anything about the original design, algorithm design or original code just by looking at the output. So this is the notion of program obfuscation. Okay, the third one is another very like this primitive is very close to my heart. It's the primitive of deniable encryption. So what does this mean? Okay, so we have lots of news where you know or lots of sort of events in history where there are protests, right? Sometimes they are illegitimate, they are also sometimes legitimate, like our own independence movement. So there may be messages that you want to exchange in a secret way, which should be deniable even given a key somehow. So I am going to not be very precise about this. So what I said was already a little bit imprecise, but the situation I am targeting is the following, right? Let us say that I send a message, I encrypt it, okay, and now someone comes and puts a gun to my head and says open this ciphertext. So you know, what will you do against something like that, right? So it seems like this is something that you should not be able to protect against, because all security, when we think of it, it's when you know the key is secret or the randomness is secret. But if somebody is forcing you to reveal that, then what can you do? So it turns out that there is a very interesting primitive that we call deniable encryption that actually allows you to deny what you said. So for example, let us say you know I encrypt some message which is controversial. Okay, so I use some randomness R during this encryption. By the way, encryption will always have to use randomness, we will talk about that later, but it can never be a deterministic algorithm. So it is a randomized algorithm and I encrypt using some randomness, right. It turns out that under coercion I have a way, depending on the scheme that I am using, I can construct a scheme which allows me to instead sample a different randomness R prime, such that the same ciphertext can be explained using this different randomness and a different message, of course, right. So basically I have some message comma randomness which was used to generate the original ciphertext, and now what I can do is I can change both the message and the randomness to be something that is okay for me. So this is something which you know, I feel that actually with most of cryptography, I think that when you first see the idea, like one is not sufficiently surprised. So this should be actually very surprising. Why should it be surprising that you can do this? Okay, so he says they won't get the actual message, but I mean that is the goal. Okay, so he says that well, you know, encryption sounds like it should be a one-way process. That's of course true, because you should not be able to invert a ciphertext, and this seems weird because it seems like you are offering two different branches to arrive at the same point. You know, I am not joking. So the more I teach, the more I feel that actually we do a disservice even just by somehow teaching, because so many of these things are so surprising, but you know we tell them to you, and thereby they lose the factor of surprise completely. But though I would like to go, you know, puzzle by puzzle and let you have your aha moment, unfortunately the schedule does not permit that. So yeah, this is some sort of fast forwarded version of that. Why is this something you would not expect, you should not expect? The reason that you should not expect such a thing to be possible is because encryption is encryption only if there is a decryption, right. It is only meaningful if there is a way to get back the original message. So you know, if I am encrypting some message M, and you know you are supposed to, somebody is supposed to decrypt it, right, otherwise what is the whole point of it? So if I am encrypting a message M, then I should have a guarantee that somebody decrypts it to M, but here I am saying that, oh, you know, actually maybe it was M, maybe it was M prime, maybe it was M double prime. So what does that mean? Who is going to decrypt it? What will it decrypt it, what will it get decrypted to rather? right? So when someone decrypts it, where does it go? So this is the sort of the issue with this. So this particular notion which I am showing you is sender deniability, okay. This is a problem I have worked on and not fully solved, and I really love this problem. So this problem is saying that, you know, the sender, so when I am the sender, let us say I am sending a message to Akhil, I do not have his secret key, right, I only have his public key, I am encrypting with his public key. If someone puts a gun to my head, I am not even expected to produce a secret key. So when you ask me how did you produce the ciphertext, the only thing I can ever show is a randomness. So what you need here is, it's only that I should be able to produce a message and a randomness that gives the ciphertext. Now what about decryptability, that's completely at the moment up in the air, but in order for the scheme to be functional, you also obviously insist on decryptability, right. So what does that mean? That given the secret key, I should nevertheless open it only to the correct message, and this is surprising. So it turns out it's very, very elegant. It turns out that, you know, it really basically for an overwhelming fraction of random coins, it will open to the correct message, but there is some very, very you know, small space of randomness which I can myself engineer in some way that I can do this, but the decryption algorithm will you know, it will work correctly for the overwhelming fraction of random coins. So basically what this will imply is that the probability of decryption, correct decryption, cannot be 1. It can be very big, like let us say it is 0.99 or something. Actually that is not very big, that is a constant factor away, that is not typically good enough, we will get into that, but it's, you want it to be tending to 1 really quickly, right, but you it cannot be 1. The question is that then when you are coerced also, why doesn't it you know, lead to the correct message? That is because I have to design the scheme in such a way. So you are right that it is not that I take any old public key encryption scheme and this thing will work. So designing a deniable encryption scheme that allows this property is a significantly challenging task, and in fact one that has not been solved in a perfect way. So we do have, obviously this course is not the place to go into this, but it is a difficult problem. There is some measure of success that we can have in this, but the answer to your question is that I have to choose a different message. I can remember the old randomness that I used, and I can sort of change the randomness in such a way that it lets me open it to a different message. So I will do this bit by bit, for instance. So you know, for every bit I have that option. Okay, very good question. So she asks, is this a 2-level encryption, one inside the other, or is it the same one? So yeah, as I said, it is a fairly sophisticated object. It is the same, there is one encryption algorithm. There is a notion of public deniability and secret deniability, where in the secret deniability case you are allowed to remember the randomness that you used before. In the public deniability case you do not even remember that. Let me just finish. So the encryption algorithm in the public deniability case is the same. In the secret deniability case, you know, maybe you can have different encryption ways of doing encryption, but it is not that you can just nest encryption schemes and get it to work. So like I said, it is actually a fairly complex problem. Yes.
So what do you mean by randomness in this exactly? You mean the key generation process?
No, very, very good. So no, I do not mean the key generation process at all. What I mean is simply the randomness that is used during encryption. So maybe this is a good time to talk about why encryption must always be probabilistic. It's because no matter how sophisticated is my mapping from whatever from my input alphabet to my output alphabet, I mean the two alphabets could be the same, but whatever, however sophisticated is my mapping, if you do a deterministic mapping, then there is a very trivial attack, and that is for instance like statistical attacks, like for instance the letter E occurs most frequently in the English language. So what do? You just sit and count which is the letter that is appearing most often, and then you map that to E and so on. So this is not a so this is not a fully formal reasoning, because I can't talk formally because I haven't even defined what the security is, right. So we'll do that later, but this is the intuitive reason. So this is why encryption has to be probabilistic. So that means that it's a randomized algorithm, it will sample some randomness and then it will take a message, the message won't be random, it will be whatever you want to say, which may be random, but at least it's whatever, it's each person's distribution. So that plus this uniform randomness will give you the ciphertext. Okay, I hope that everyone got confused, because that is the, it is something to be surprised by. So even if not confused, but I would like people to appreciate why these things are surprising, and in fact all of cryptography is very surprising, all of it. The existence of encryption is very surprising, right. The existence of one-way functions is surprising. What are one-way functions saying? That somehow we live in a universe which has a computational asymmetry. Something is easy in one direction and hard in the other direction. Why should it be like that? We have no proof. So who knows, maybe it's not. I mean, for instance, like even the arrow of time, right, from what I understand, there is no reason for it to only go forward according to the math, but that's our empirical experience, that's our experience. But so similarly with one-wayness etc., we don't really have proofs that it has to be like this, but that is what we observe and we try to make use of it. Okay. The fourth one, so computing on encrypted data. So this is also something that I actively work on. So what this is saying is that typically you think of encrypted data as being like it should look like I don't know, junk, right. I mean, it's not supposed to leak anything about what's inside it. So maybe a simplistic way of thinking about it is that the ciphertext should be indistinguishable from random. We haven't even defined indistinguishable, everything needs to be defined, okay. We'll do it slowly, but one way of thinking about it, like I said, is that basically all my ciphertext should look like random elements in the space. But if that's the case, then it shouldn't be good for anything except decryption, right. Basically, okay, I know I can decrypt it, which is surprising in itself, as I said, that public key encryption should exist. These are, by the way, Turing award winning ideas, like these are very significant ideas, but fine, we've gotten past the fact that we can decrypt. Now what we are saying is that not only can we decrypt, we can actually compute on it while it is encrypted. So there is a way for me to take a bunch of ciphertexts. Again, not any ciphertext, I have to design the scheme in this way, but there is a way for me to take a bunch of ciphertexts and actually do meaningful arithmetic with it. Okay, so if you want to run machine learning algorithms on data while it is encrypted, it is possible, at least in theory it is possible. Okay, so one motivation for this comes from the cloud and so on, but forgetting all that, mathematically it is very interesting, right. the concern is that, you know, can't then if I have this way of encrypting, sort of computing on encrypted data, then doesn't this open up the following attack scenario? I can now keep computing on it and sort of bring it to a point where it is far removed from the original data. This is the question. So the answer is that this is not in any way an attack. I mean, who is the person or what is the entity who is computing on the data? The data is encrypted and it is stored, you know. Let's say that I put it up here on my blackboard, the encrypted data. Now if you take it and do something with it, it's up to you, right? I mean, it's not in any way harming the data that is that has been stored or published or whatever. Is that can you think of a attack scenario where being able to compute on it is a problem?
Visible to you.
Right, good. So the question is that, well, if the attacker can mess with the data, they may not know what it is, but they can make it unusable to you. So you are absolutely right that there are scenarios where you don't want your ciphertext to be malleable. Right. So the example of storing data in the cloud and computing on it, etc., in that sort of a scenario, if I download the data and mess with it, it doesn't hurt anybody. But for instance, you know, if I think of two people communicating, right, this is the example I usually don't like, but if I think of two people communicating and an attacker sitting in the middle intercepting the communication, what you could do is potentially change the data without me even realizing, right? Like maybe you sent me some message and then somebody else you know, changed it in a way so that it is still decryptable, but then now I am decrypting it to something that it was not meant for. So that's absolutely true. The answer to this is that you know, the in cryptography, even in encryption, let's focus on encryption, there is never a one size fits all. There is never a one thing which is good for, there is no one scheme which is good for everything, right. So if you are in an application where you need you need message integrity, note that encryption schemes provide privacy and not integrity. So if you're in a situation where you need integrity, then you have to you know, use the appropriate cryptography that will guarantee integrity. For instance, you have these things called message authentication codes, or you know, just forget even that, just hashes. For instance, right, I could sign the ciphertext that I sent. I guess hash, I was thinking of hash, but in this situation maybe even hash doesn't solve it, because if I hash the ciphertext and send it, you could change the ciphertext and recompute the hash, for example. But let us say that I sign it and send it, right, then you cannot forge my signature. So the point I am making is that you need different cryptography to achieve different guarantees, and the setting of encryption is not one that gives you integrity. And really there is a lot of work that is there just in modeling the attack scenario mathematically, like what is it that you are worried about, right. There are different worries in different cases and you have to model that correctly.